Okay, good morning and welcome back to our Teknik Digital course. And I believe this is our 12th class. So today we're going to discuss about the concept of sequential machine. In our previous recording, we discussed about flip-flop, where we are discussing about flip-flop because flip-flop is the main foundation or the basic memory of the sequential machine. So that's why today in this recording we're going to discuss about the sequential machine. Okay, let's just move on to the flip-flop. Now, in our previous recording we discussed about there are three kinds of flip-flop. The first one is the data flip-flop, and then the second one is the JK flip-flop, and then the last one is the toggle flip-flop. In data flip-flop is something like I want to store something, please store this, and if I want to retrieve my previous data, I'm going to get it from the output. So that's why every time I send 0 as the data, the output will become 0. And when the data is 1, then the output will become 1. So it's just something like storing the data. So that's why it's called data flip-flop. And then for the JK flip-flop, we have several modes. We have the when j is 0 and k is 0, the output will remain the same. This is what we call the hold mode. And then when j is 0 and k is 1, the output will become 0. This is the set mode. And then when j is 1, k is 0, the output will become 1. This is what we call set mode. The output will become set 1. And then when j is 1, k is 1, the output will become the opposite from the previous output. So that's why it's called toggle. So when the output is now 0, clock, it will become 1. Clock, 0. Clock, 1. Clock, 0, etc. That's what we call it called toggle mode. And the toggle flip-flop is a simplified version of the JK flip-flop, where when t is 0, the output will remain the same, hold mode, and when t is 1, the output will become the opposite from the previous output, which is what we call toggle mode. Okay, this is what we learned from previous class. Data flip-flop, JK flip-flop, and also the toggle flip-flop. Now, the sequential machine. Sequential machine, or in this case, we're going to call it finite state machine because it has a finite state, not unlimited state. We can have several states for the machine. And the main difference between FSM and then the combinational logic, well, actually, an FSM is comprised with the combinational logic and also the memory. And this memory will be implemented using the flip-flop. So it's something like if we combine combinational logic with flip-flop, we can get the finite state machine or sequential machine. And the main difference between FSM and pure combinational logic is the first one, if we change the input, then in combinational logic, the output will also change. This is for the combinational logic. However, if we are using the FSM, if we change the input, the output will change only if the clock active. So when the clock active, then the output can change. Okay, this is for the FSM. For the first difference between combination logic and the FSM. And the second difference is in combination logic, the output depend only from the input. So combination logic is a function from input to output. So that's why the output only depend on the input. So when the input is, for example, 0, 0, 1, then the output will be definitely one value, either 1 or either 0, depend on the function. However, in the FSM, the output depends from the input also, and also from the previous output. So it's something like clock. The output will become what? Well, it depends on the input, and also it depends on the previous output. So that's why we need something that we call memory to memorize what is the previous output. What is the value of the previous output? Okay, so that's the two differences between combination logic and the FSM. First one is based on the changing of the input. In combination logic, if we change the input, the output will change. But in FSM, if we change the input, we need to activate the clock to make the output change. And then the second difference, in combination logic, the output depends only on the value of the input. But the FSM, the output will depend not just the value of the input, but also the value of previous output. So that's why we need to store the value of the previous output using the memory. So that's why the output of the FSM will be feedback to the memory to remember this is the value of previous output. Okay, that's the two differences between combination logic and the FSM. Now we have two types of FSM. The first one is melee, where the output depends with the input and the present state, and the more is simplified from melee model, where output state depends only with the present state. So what is present state now? This is the melee model. As we can see in here, we have something that we call combination logic. So this is the combination logic. It's just like AND gate, NAND gate, OR gate, NOR gate, SOR gate, inverter, etc. That is combination logic, and we call it next state combination logic. Why? Because it will calculate what is the next state value. What is the value of the next state? So that's why it's called next state combinational logic. And then we also have the output combinational logic. It will calculate what is the value of the output based on present state and also the input. So this is the input. Then the flip-flop will be in here. The output of the flip-flop, the Q of the flip-flop, will store the value of present state. And the next state is the input of the memory of the flip-flop. So it's just something like, this is the value of next state. Please calculate what will be the present state. This is melee model, and the more model is a simplification of the melee model. Something like this. So the difference is there is no calculation of the input to create the output. So the output in here only depend on the value of the present. So this is more model. Okay, so this is melee, this is more. Okay, now we're going to discuss about something that we call state, because we have next state and also the present state. As we can see from the earlier block diagram, the present state and also the next state is based on the flip-flop. So if we have one flip-flop, then there will be only one Q here. So the present state will be either 0 or 1. However, if the memory has two flip-flops, so there will be two Qs. We can call it A and B. So you can have either 0, 0, 0, 1, 1, 0, and also 1, 1. So it has four present state. It has four states, but in here they only have two states. Now the three states, we can call it A, B, C. This is what we call variable states. So A, it's a variable state. B is also a variable state. C is also the variable state. Okay, so let's think about, okay, now the value of the Q or the output of the flip-flop is 1, 0, 0. Now, wow, it will change the state to become 1, 0, 1. That means this is A, this is B, and this is C. So A right now is 1, 0, 0. A is 1, B is 0, C is 0. Clock A will remain 1, B will remain 0 in here. This is A, this is B, but C will change to 1. This is after the clock. So the state right now is 1, 0, 0. Clock, it will become 1, 0, 1. Clock again, it will become 1, 1, 0, 1, 1, 0. So B will change to 1, C will change to 0. And then clock again, it will become 1, 1, 1. Clock again, 0, 0, 0. Clock again, 0, 0, 1, etc. Okay, this is what we call sequence of states. The change of the state will be based on the clock. Clock, the state will become 1, 0, 1. Clock, the state will become 1, 1, 0. Okay. So, how many states does an FM have? That depends on the maximum. Sorry, that depends on the number of the flip-flop. So, let's say I have a state diagram, or I have a finished state machine that has 3 states. That means I'm going to need 2 variable states, because using 2 variable states, let's say A and B, it can have 0, 0, 0, 1, 1, 0, and also 1, 1. This is 4 states. And we need only 3 states. So we can choose this one. Or we can choose this one. Or either one. Okay, that's the number of states. Now, this is an example of state diagram. State diagram explains how the state change when it receives a clock. Okay. Now, for example, I am right here. This is the present state. 0, 1, 0. So this is A, this is B, and this is C. And then clock. It will change to A will remain 1, B will change to 1, and C will change to 0. And then clock again. A will remain 1, B will remain 1, but C will change to 1. Okay, this is a simple one-way state diagram. Now, how about this one? Right now, we are here. This is the present state. 0, 1, 0. This is A, this is B, and this is C. Clock. Where should I go? I could go either to here or to here. Depends on the value of X. X is an input of the FSM. If X is 1, then it will move to here. So it will change the state to 1, 1, 0 if the X is 1. However, if the X is 0, it will go back to here. So the state will become 1, 0, 0. So it depends on the value of X. And X is the input of the FSM. This is X. And this is X. Now, we already take into consideration about the input, and we call it the input X. How about now the output? The output, we can call it Z. And Z is active if the present state is 1, 1, 1. So A is 1, B is 1, C is 1. Okay. So now, let's say for example, this is where we are now. 0, 1, 0. Clock. What is the value of X? X is 0, so I'm going to here. So the state will become 1, 0, 0. Now, clock, what is the value of X? X is 1, okay. Now I'm going to return here, 1, 0, 1. Clock, what is the value of X? X is 1, okay. I'm going to here now. Clock, what is the value of X now? X is 1, so I'm going to change to here. So we reach the state where the output Z is active. So the Z or the output will active when A, B, C, all of them are 1. This is what we call Moore model. For the Mealy model, the output will depend on the value of the input. So it will become something like this. Z is active if X. Okay. So, for example, we are here. 1, 0, 1. Clock. X is 1. Okay. We move here. 1, 1, 0. Clock. We move here because X is 1. 1, 1, 1. Z is active. What is the value of X? X is 1. Okay, Z is active now. However, if X is 0, then the output will not active. Okay, that's it for the discussion for today, because after this, we're going to learn about how to design the FSM. At least now we have the foundation. The first is we have two types of FSM. The first one is Mealy, and the second one is Moore. And we also discuss about what is the difference between FSM and combination logic. We have two differences. And then we also discuss about states and what is the relation between states and the flip-flop, and then how the states change. Starting from the simple one-way state diagram using only clock, independent with the input, and then two-way state diagram using one input, and in this case is X. And then we also discuss about the state diagram where we have the output also, including the Moore model and also the Mealy model. So next week we're going to discuss about how to design the FSM, starting from the how to design state diagram and then how to design the FSM. Okay, I think that's it for today for this recording, and don't forget to do the quiz. Okay, thank you and bye.